Okay, welcome back. And today we're going to start chapter 7. And this is going to be about graphs, functions, and linear systems. And so 7.1 is just going to be about graphing and functions. Okay, so that's going to be what we're going to cover today in this section. So 1, we're going to plot points. So we're going to be able to plot points in a rectangular coordinate system. 2, graph equations in the rectangular coordinate system. What is a rectangular coordinate system? We'll discuss that. Use function notation, how to use function notation, how to graph functions, how to use the vertical line test, and 6, how to obtain information about a function just by looking at its graph. So now, the points and ordered pairs. So on a rectangular plane, you can determine the location of any point by just 2 coordinates in the x direction and the y direction. So the way this is built, the coordinate system, the rectangular coordinate system has 2 axes. You have the x and y axis. So with these 2 axes, we have the x-axis, which is the horizontal, and we have the y-axis, which is the vertical. And so I can determine the location of any point anywhere in this plane as long as I know how far to go in the x direction versus how far to go in the y direction. Okay, and so the origin is going to be the middle where the 2 axes intersect. That's the origin. It's always 0, 0. That's our starting point. And so we also, the axes, as you can see, divides the plane into 4 quadrants. And it always goes from the first quadrant here, which is positive, positive. So in the positive x direction, the positive y direction, that's quadrant number 1. And it goes counterclockwise around. So it's 1, 2, 3, and 4. Okay, and so you can also determine what quadrant a point is located just by knowing the sign of each coordinate, because in the first quadrant both the x and y coordinates are positive. And so before I go any further, the x coordinate is the first coordinate in the ordered pair. So in this example here, this represents the xy coordinate 0, 0. So the first number is the x direction, and the second number is the y direction or the y coordinate. And so if they're both positive, then we know that you're in the first quadrant. If the x is negative and the y is positive, then you're in the second quadrant. If they're both negative, you're in the third quadrant. And if x is positive but y is negative, then you're in the fourth quadrant. And so just by looking at the signs or the combination of signs for the ordered pair, you can see or tell which quadrant you're located in. And so, for example, here we have these 2 ordered pairs. So here's the xy pair, and we have -5, 3. So that means -5 in the x direction, which means we're going to the left in this case, and we're going up 3 units. Versus if we flip the signs and we said, okay, 3, -5, and we flip the ordered pair, well, these 2 ordered pairs are not the same, because this means 3 units to the right and 5 units down. Okay, and so look at the picture here. So this is where -5, 3 is going to be located, and 3, -5. So if you switch the xy coordinates, then you get a completely different point on the coordinate plane, the rectangular coordinate plane. Okay, so now if we plot the points A, B, C, D, E, and F, well, then we just use the xy coordinates, and we just understand how to plot these by realizing that the first coordinate is your x direction, which means you're either going to go left or right, and the second one is your y direction, your y coordinate, and so you're either going to go up or down. So right is always positive versus up is always positive. So if it's positive here, then you're going to be going right. If it's negative, you're going left. And then here, positive is in the up direction, negative is in the down direction. Okay, and so now that we know that, we can say, hey, all of these points means that we're going to go 3 units to the left, 5 units up. And so there's where we mark A. And then B is 2, 4, which means 2 units to the right, 4 units up, which means we're going to be where? We're going to go, oh, hold on a second. Oh, this should be -4. That's a typo. So that should be -4. So 2 units to the right and 4 units down. So this is correct, but that's a typo. So it'd be down here. So here's B. And then 5, 0 means that, hey, you're not moving anywhere in the y direction. So you're just moving to the right 5 units. And so there it is. And then you have these, and so on and so forth. So you can see how these are plotted. Okay. Now, a relationship between two quantities can be expressed as an equation in two variables, such as the equation we have here. Okay, so a solution of an equation in two variables, x and y, is an ordered pair of real numbers with the following property. When the x coordinate is substituted in for x in the equation, okay, or excuse me, I'm sorry. Yeah, that's right. And the y coordinate is substituted here for y. Then if you solve both sides of the equal sign, you will get the same number. Okay, so you will always get a true statement. You will get 3 equals 3, or 4 equals 4, or 10 equals 10. But both sides of the equal sign will always give you the same number. Okay, so that's by what we mean by a solution. Okay, so if a solution, if an ordered pair is a solution, we can plug in x and we can plug in the y, and we'll end up with a true statement. Okay, now the graph of an equation in two variables is the set of all points that satisfy this property. Okay, or in other words, satisfy this equation. So we take all such points that satisfy this equation, and that's going to give us the graph of the equation. Okay, so when we talk about a solution set and we talk about a graph, those are two different things, but they're directly related to each other. Okay, so here, if we want to graph this equation or this relationship, we select integers for x. So we just basically select a bunch of integers for x. And what we do is we plug in that value for x into the equation and see what value of y we get. Okay, so for example, they start with -3. And so -3, we plug in -3 into this relationship, this equation. And what do we get for y? Well, we get -5. Okay, so the ordered pair that lies on the graph, or the ordered pair that is a solution to the equation, is -3, -5. And when we do that again for -2, okay, just plug in -2 and solve for y, and we get 0. So -2, 0 is also a solution. It's also a point on the graph. And we do this over and over again for different values of x. We're going to get all these ordered pairs. And when we plot these ordered pairs on the rectangular plane and then connect them with a smooth curve, with a smooth line, we end up with the graph, or a sketch of the graph. And so in this case, we end up with something that looks like this. Now, if an equation of two variables, x and y, yields precisely one value of y for each and every value of x, we say that y is a function of x. So it's a special relationship. Not all relationships are functions. Okay, so if for every value of x that's given, there is exactly one value of y, then there is a function. We say that y is a function of x. And the notation is given by this f of x. And that's how we pronounce that. It's this symbol here. So we say y is a function of x, and we say this is f of x. Okay? And so that's how we pronounce it. Now, tailgaters beware. If your car is going 35 miles per hour on dry pavement, your required stopping distance is 160 feet, or the width of a football field. Now, at 65 miles per hour, the distance required is 410 feet, or approximately the length of 1 1/10 football fields. Okay. Now, figure A on the next slide shows stopping distances for cars at various speeds on dry roads and on wet roads. Now, figure B on the next slide uses a line graph to represent stopping distances at varying speeds on dry roads. So let's look at those. Okay, so now look. So this is on dry road. See, so this teal or green is on dry roads, and the blue is on wet pavement. So dry pavement versus wet pavement. Okay, so notice that the stopping distance is obviously longer or larger than on wet pavement as it is on dry pavement, which is to be expected and makes sense, right? Now, if we look at the line graph here, so we plot each one of these points, each one of these stopping distances on a coordinate plane, and that's what represented by each of these dots, and we draw a curve through the dots, we get a graph of stopping distances on dry pavement based on speed of the car, right? And so this would be the graph that would represent stopping distances on dry pavement. Now, A says use the line graph to estimate a car's required stopping distance at 60 miles per hour on dry pavement, and then round to the nearest 10 feet. Okay, so if we go back, and so here's 60 feet, or 60 miles per hour rather. So if we go up here to the line, we notice that how many feet is that? Well, if we want to estimate this, well, what do? We're right about, I'd say 360 feet, right? We're a little bit past halfway. I'd say 360 feet. I mean, that would be my guess to the nearest 10 feet. And so look at this. So approximately 160 feet. So at 60 miles per hour, based on this graph, you should allow 360 feet stopping distance. Okay? And that's how they conclude. Okay. Now, B says, okay, now we're going to use this function of x, okay, that models the required stopping distance, f of x in feet. Now, on dry pavement, traveling x miles per hour. Now what we're going to do is we're going to use this function to estimate the stopping distance needed when you're going 60 miles per hour to the nearest foot. So now we're going to round to the nearest foot. So all we have to do is plug in 60 into here, which we get 3,600 here. So 3,600 times this minus this, right, plus this. So whatever, we just plug in for x, and we plug it into our calculator. And so what do we get? Well, we just plug in 60. So the thing is wherever x is, we're going to replace that with 60. So here, we're going to replace this x here with 60. So we're going to get x quantity squared. And then here in these parentheses, we're going to put in 60. And so now we're going to plug this into our calculator and simplify. Right? And so we get this here, and our final answer is going to be 357.6 feet, or approximately 358 feet of stopping distance. So based on our estimate, based looking at the graph, wasn't bad. We weren't off at all. I mean, hardly. But using the function, we're more accurate. With the graph, we had to use, we had to round to the nearest 10 feet, but we actually did pretty well. Okay. Now, graph the function. So what we're going to do is now we're going to graph these two functions. We're going to graph the functions f of x equals 2x and f of x or g of x equals 2x plus 4. So the only difference between these two functions is that we're adding 4 to g of x, okay, with g of x. So in other words, what we're doing is we're taking f of x. You could look at this as this is f of x, right, is equal to this. So you could look at this as g of x is equal to f of x plus 4. So what's that going to do? Well, let's find out. So we're going to do all the integers from -2 to 2 inclusive, and we're going to plot those on a table. So for each one, we find the ordered pairs, right? So we plug in the same x values into both, and we get the ordered pairs, right? And then what we do is we're going to plot those ordered pairs like so. Now, next, plot the 5 points for each function. So we plot this one, and we plot this one. Okay. Now, if you look at these two, do you see a relationship? Now, some of you would probably look at this right away and say, oh, one is moved to the left. So g of x is moved to the left 2 units versus f of x. And you're right in a sense, but that's not actually what's going on. It's actually being moved up. This point here is being moved up 4 units. Okay, because what are we doing? We're taking the f of x, we're taking all the points of f of x, which is a y value, right? F of x is equal to y. And we're adding 4 units to f of x, which is basically adding 4 units to y. So that means we're moving up 4 units. So each one of these points is moved 4 units up. And so this is actually a motion, or what we call a translation, of up and upward. So we're moving the graph or translating it upward. Okay, now the vertical line test for functions. So the vertical line test is an easy and quick way to determine whether you have a function or not, right? Remember, the definition of a function is that for every x value that you plug into the equation or into the relationship, you only get one y value out. Okay? Different x values, okay, may give you the same y value, or they may give you different y values. The point is that for each and every x value, you only get one y value. You don't get any more. You get, at most, one y value. Okay, so now the vertical line test says, hey, if I can draw a vertical line anywhere in the graph, and it only intersects the graph at most one location, one point, or once, then it's a function. If I can draw a vertical line somewhere where it intersects the graph at more than one point, it is not a function. So if we look at A, I can draw a vertical line, right? So can I draw a vertical line that intersects at more than one place? And the answer is yes. I can draw right here, right? Or I can draw right there. And so it intersects here and here. So since it intersects at more than one place, it's not a function. Now what about this one? Can I draw a vertical line anywhere that intersects at more than one place? And the answer is no. Right? So no matter where I draw a vertical line, it will only intersect the graph once. Same here. Right? Now here, for D, can I draw a vertical line that intersects at more than one place? And the answer is yes. I can intersect here and here. And so therefore it is not a function. Okay? I hope that makes sense. So now, if we're given it a graph, okay, so let's, given the graph, this graph illustrates body temperature from 8 a.m. to 3 p.m. Okay, so let x be the number of hours after 8 a.m. So the number of hours that have passed since 8 a.m. And y is the body temperature at a particular time x. Okay, so now A says, what is the temperature at 8 a.m.? Well, from the graph, the temperature is what? 101 degrees what? Fahrenheit. That's at 8 a.m. because at 8 a.m. x is 0, right? During which period of time is your temperature decreasing? Okay, so if we look at the graph, the temperature is decreasing from here to here, right? It's not decreasing anywhere else. It's just from here to here. So from 0 to 3, right? So which period of time? It would be from 8 a.m. to 11 p.m. or excuse me, 11 a.m. So 8 a.m. to 11 a.m. your body temperature is decreasing, or this body temperature is decreasing. Okay? And then C, estimate your minimum temperature during the day, during the time period shown. How many hours after 8 a.m. does this occur? Well, the lowest body temperature, as we saw, is right here, 3 hours after 8 a.m., which is at 11 a.m. Okay, so it occurs 3 hours after 8 a.m., which is 11 a.m. in the morning. So 11 in the morning is when the body temperature reaches its minimum value. Oops. Okay, now, during which period of time is your temperature increasing? Well, from here, it's increasing, right? It's going up. So from hour 3 to hour 5, it's increasing. So that would be from 11 to 1. So from 11 a.m. to 1 p.m., the body temperature is increasing. Okay. Now E says part of the graph is shown as a horizontal line segment. What does this mean about your temperature, and when does it occur? Okay, so this horizontal line, is the body temperature changing? Well, no, it's staying the same, right? It's staying right at 100 degrees Fahrenheit. So it's not increasing or decreasing, it's constant. So that's what it means. It means that your body temperature is constant during that time period. And what time period is that? Well, it's from the the 5th hour after 8 and the 7th hour. So that's going to be from 1 p.m. to 3 p.m. that your body temperature is constant. Okay. And then finally, it says explain why the graph defines y as a function of x. And the quick answer is the vertical line test. You could draw a vertical line anywhere on this graph, and it will only intersect at most one place on the graph. Okay? Okay, so there are the solutions. Did they ask that? Hold on. What does this mean about your temperature? Oh, E. Oh, hold on. Oh, I forgot. It says estimate your minimum temperature during that time. So the minimum temperature was what? Well, if we look here, we go straight across. We're at what? This is 98 and 99, so we're a little more than halfway, so 98, 98.6, which is, we already saw the answer, but that's correct. So 98.6 at 11 a.m. Okay, and let's see here. Okay, we did that one. Okay, and hold on. Okay, and that wraps up this section of Chapter 7. Okay, so again, I'm going to repeat myself. Make sure you go through these examples. Go through the examples, other examples in the textbook, and make sure you can do them. Go through the suggested homework problems. Make sure you can do those. If you get stuck, or if you have any questions about this video or the problems that you're working on, whether it's the homework problems, or the quiz, well, not the quizzes, but um, the homework on My Math Lab or anything like that, please make sure you bring those to class, because those are the ones we want to work on first. So the more questions you have, the more problems that you get stuck on, the more that we can help, and that I can help you get over the hump, and that you can be more successful. So again, we're going to be ready to work. So again, do your due diligence, watch the videos, and then when we get to class, we will jump right in and start working. If you have any questions, you can email me, of course. And other than that, I'll see you in class. Have a great day.